Yeah, happy to invite our fourth speaker for DOCUS this year. So Claudiu Raicu from Notre Dame is gonna be giving the first of a couple of talks on computing local Euler obstructions.
All right. Well, thank you guys for putting this together and for giving me the opportunity to talk. So I just want to talk about this very interesting invariant, and it's used in singularity theory, intersection theory, and it's closely related to the modules. So I want to first spend some time introducing it. So, so what's the setup for me? X is going to be a smooth, complex algebraic variety. And then to any subvariety, or more generally closed subset, V in X, what we can do is we can associate a constructible function from X to the integer. So this just means it's constant along some stratification of X. And it's called, so this was introduced by McPherson in the 70s. And my goal is to give some definitions and try to compute it in some example. Okay. So before giving you the definition, let me tell you some properties. So, well, you could think of it as really just a function on the subvariety, because it always vanishes outside V. Moreover, this is equal to 1 for a smooth point. And then it's going to be constant along any sufficiently nice stratification. So let me just say that this is constant along the strata of any witness stratification. But anyway, basically any stratification you think about in nice examples would have these properties. And just for a very concrete example, so let's take V to be the affine cone over a plane curve over a non-singular degree D. Curve in P2. Then because the value of the Euler obstruction at the cone point, this was going to be 2D minus D squared. And so I just want to emphasize that this number may be negative. And it's not going to come up today, but it will come up next week when I talk about some more general examples. Okay, so at least we computed this local Euler obstruction in one example. And so then what do I want to do is, I want to fix a stratification of my space X. And which is nice enough. And then what I can do is I can just define this numerical invariance. So EIJ is you take the closure of a stratum, you take the Euler obstruction function, and you evaluate at any point in the stratum. So, and the goal is to just compute this matrix, these numbers explicitly. And nice examples. And well, just to have some in mind, and I'll go into more details. But for instance, I like the matrix rank stratification. Or you take a flag variety, look at the Schubert stratification. Or maybe, in general, whenever you have a group action with finite many orbits, maybe a toric variety or something. Okay, so there's lots of natural examples to consider.
Sorry, could I ask a question?
Yes.
So this EIJ will depend on the choice of xi, the point xi?
So so I'll always take my stratification. Well, of course, it will depend because, it's the Euler obstruction of the variety xj bar, yes. But I guess what I'm saying is that if, for instance, I break up the stratum xi a little further into pieces, but I keep xj if I keep, I'm not saying anything interesting. I'm just saying that this function depends on the subvariety, as EU of xj bar depends on xj bar. So I guess if I choose a different stratum whose closure is still xj bar, so if I break it up in a different way, and I get a stratum whose closure is who's still dense in xj bar, then the values are going to stay the same. So, they have to depend somehow on the stratification because.
So I wasn't worried about the stratification, but more the choice of point xi.
Sorry, the choice of point. I missed this. No, sorry. So I'm taking a nice stratification, a Whitney stratification, and then the statement is that this is constant along the stratum. So it doesn't depend on the choice of the point.
I see. Okay,
yeah, so sorry, I misunderstood the question. Yeah. All right, so let's just do an example based on the properties I talked about earlier. So let me just take maybe let me just take projective 3 space. And let me choose a stratification where I take a quadricone, and then inside it I pick a line, and then I choose the cone point over here, right? So I guess this would be the stratum x0, the green one would be x1, the quadricone would be x2, and then you get everything else. Okay, and my claim is that the matrix that you get from here is the following shape. It's upper triangular, and most of the entries are going to be equal to 1 because most of these orbit closures are going to be non-singular. The only orbit closure that has a singular point is the closure of x2, the quadricone, which has the singularity at the cone point. And this 0 over here is going to be just 2d minus b squared, where d is equal to 2. Okay? So, and again, the ones, this is the property that if I evaluate the Euler obstruction of the non-singular point, I get that. All right, so maybe just with these examples in mind, maybe it's time to give a definition. I want to give a definition in terms of D modules or reverse sheaves. Hopefully there will be more definitions next time. This is the one we're going to work with today. So it comes from the following commutative diagram. So we all know the Riemann-Hilbert correspondence between regular holonomic D-modules and reverse sheaves. So this is an equivalence, so you may choose which side you're more comfortable working with. And now there's a map to the free abelian group of Lagrangian cycles in the cotangent bundle of X. So what this group is just a free abelian group generated by cotangent to subvariety units, cotangent bundles. So really what I mean here, I just take the regular locus of a subvariety V. I look at the cotangent bundle of that and take the closure. Okay? And what this map is for D modules, this is called the characteristic cycle. And just, or sometimes singular sports, I mean, these two names are used interchangeably, so I guess I'll use characteristic cycle for the D modules and I'll use singular support for the reverse sheaves. Okay, so we have a commutative diagram like that. But then we also have maps to constructible functions. Which you should think of also as a free abelian group generated by the the indicator function for a subvariety. And let me just write the map this way, so I don't put too many errors. So this is just the stock Euler characteristics. So if you take any perverse sheaf X, or like the Theorem complex of a polynomial module, then you could look at a function which at the point X in X is just defined as the, well, you take the sheaf, you look at the stock, and then you look at the Euler characteristics. Like this. Sum of -1 to the I as the dimension. The ith cohomology of the stock. So again, this, I think of it as a function from X to. So if you like the module, I mean, take the Theorem complex, look, take the stock and compute this Euler characteristics. And so how does the Euler obstruction show up in this picture? So this Euler obstruction function give a different basis for the set of constructible functions. And it is the basis that corresponds to the cotangent bundles of subvariety. So the statement is that there exists an isomorphism between these groups. So of course, there's an obvious isomorphism that takes the indicator function to the cotangent bundle of V, but there's one that makes this diagram commute. And what this is going to do is we will send the Euler obstruction function of V to the cotangent bundle up to a sign. So I think there is different conventions, but I'll just take -1 to the dimension of V. So this is the unique function. Such that that gets sent to, just basic unit vector in this Lagrangian set. All right, so maybe let's do one more example. So that we see this 2d minus d squared showing up. So let me take now x to be just affine space, and I'll take v to be the cone over, so this is affine cone over the degree d plane curve. And so I promise you're supposed to get 2d minus d squared. So in this commutative diagram that I had on the previous page, so I started with the Theorem correspondence. So here on the left, I take the intersection cohomology sheaf of V, and that corresponds to an intersection cohomology D module associated to V. It's just a simple object in the category of monomial D module. So you have a characteristic cycle map. And it turns out that you can compute the characteristic cycle of this D module or IC sheaf, and it's just, so it's always going to start off with the cotangent bundle to V. with coefficient 1, and then you also have a contribution which is supported at the singular point 0, and the coefficient here is going to be d minus 1. Okay, so that's one part of the diagram. Then you could also look at the local intersection cohomology Euler characteristics. And then, of course, what we get is 0 outside V. Then we're going to get 1 if we're on the regular locus, so we're not at this singular point. And it's just by the behavior of intersection cohomology when you take cones, the Euler characteristic is going to be 1 minus 2g at the origin. So maybe the bit numbers for the projective curve were 1, 2, g1, and then you're losing the 1 when you take this cone. And so perhaps I should remind you of the formula for, well, I should remind you that this is non-singular. And then the formula for the genus of a plane curve, which is d minus 1 choose 2. So I guess if you do the calculation over here, you get 3d minus 1 minus d squared. All right, and then there's supposed to be this other correspondence S, where this guy corresponds to the Euler obstruction function on V, and this guy corresponds to the Euler obstruction function at 0. And really what the commutativity of the diagram is saying is it's saying that if I take the local intersection cohomology stock function, then that's supposed to be exactly the Euler obstruction of V plus d minus 1 times the Euler obstruction of V. So V is two-dimensional, so that's why I don't have any signs. Okay, and then, well, you could check this. So on X minus V, nothing is going on. On the regular locus of V, so this is on X minus V, this is on the regular locus. And then at 0, well, at 0, you get maybe a more interesting identity, which is just that the 3d minus 1 minus d squared is the 2d minus d squared plus d minus 1. And so really the way you should think about this diagram is you got to know 2 out of 3 things in order to know all of them. Yeah? So it's either you know how to compute intersection, so you need 2 out of this, the following information: local intersection cohomology, characteristic cycles, or Euler obstructions. That's what the commutativity of this diagram is saying. And so I don't know which one you prefer, but I just told you what they are for the cones of the curve. Okay, so let me say this. Let me just write down what I just said. So the note is that we have a relation between 3 invariants of the stratification, so the characteristic cycles by singular support of the IC sheaves on the closure of the strata, then the stock intersection cohomology of characteristics is constructible functions. And then the new set of constructible functions, the local Eulers. And what I'm saying is that any two determines the third. So maybe there's one remark to be made, is that in the situation when the singular support, these characteristic cycles of simple modules, is in fact irreducible, then the Euler obstruction function is the same as this stock intersection cohomology Euler characteristic. So maybe I should emphasize that this is a function. This is also a function on the point. Right? And so I guess that I can suggest a more general problem than the one I considered at the beginning. So given a nice stratified space as exemplified earlier, I'd like to compute maybe all these invariants. And so to me, the interesting case is, and the one that I'm going to talk about today is this case A, where X is an affine space, and it has an action of a group with finite inner orbits. And then another example would be when X is a generalized block variety. And I'll do an example of that next time. All right. So I guess let me repeat myself one more time just to establish some more notation. So again, X is going to come with this nice stratification. And I'll write VI for the closure of the strata, and then DI for the dimension. And so I said that there's three sets of invariants, which I can encode in some matrix. One. So this is the Euler characteristics of the stalks, various points in the stratum Xi. This matrix is just the local Euler obstructions that I talked about earlier. And then this matrix M encodes this characteristic cycles of simple modules of IC sheaves. So this is, I'm just going to throw in the sign for reasons that will become obvious. So this MIJs, they just give you the singular support. This is just the sum of MIJ and the cotangent bounded to the And just a matter of terminology, these are usually called microlocal multiplet. And the statement that I mentioned earlier, that any two determine the third, is the following matrix equation, which just follows from this commutativity of the diagram. It's called Kashivara's microlocal index formula. And I'm not going to try to give all the names and all the versions of this theorem, but it goes back to work of Kashivara in the 70s, and then Gibson and Belinsky. Then Ginsburg has a maybe more algebraic demodule approach, but what it says is that the relation between these three matrices is that the chi matrix is E times M. All right, so if you're good at computing chi and M, for instance, then you find the local Euler obstructions. And so then what Andras, Lawrence, and I do is we look at the case of this matrix stratifications. So X is a matrix space, and G is a natural group of symmetries. So what I mean by that is, now either I look at M by N matrices, and then the group is GLN plus GLN, or I look at symmetric matrices, or skew symmetric, I guess. In this case, G is just GLN. And then what we do is we just give a recipe for computing all these invariants. Are based on the knowledge of the characters of simple equivariant demodules. So what do I really mean by this? I mean that from knowledge of the decomposition, so I guess you take any orbit closure, rank at most J matrices, you look at the corresponding simple demodule. I guess you take global section if you want, and this is going to be decomposed into a sum of irreducible representations. So I computed this decomposition a few years ago for different reasons. And what I'm saying is that based on this knowledge, you can use this structure to understand something about these invariants chi, E, and M. And so I think this leads to what I find to be a very interesting problem as well. So try to do the same for other pairs So again, X is some representation of reducted to G maybe, or Gx with finitely many orbits. You look at simple D modules corresponding to the closures of the strata. How can you decompose these into simple G modules? I just want to point out that at least to me, this kind of information is inaccessible if you just look at reverse shifts. I have no idea how to, just from the topological side, how to figure out this decomposition. It's certainly extra, but it's new, interesting information, and then if you know how to use it, then you can get these calculations. So we use it for other purposes, also to compute local homology and other functors, but I think this is certainly an interesting problem, how to find the characters of simple D modules. So the remark is that this decomposition contains information that is, at least to me, it's inaccessible on the perverse shifts. So the results themselves are, they're not particularly new for the matrix spaces. So these computations appear based on different methods in several different papers. So definitely, for singularity theory, we did, I think, the general matrix case, and then once upon, as a student of Rimani, they do the skew symmetric case. And there's a recent paper in the Jan who actually does all of the matrix space. So I made a comment here that in this case where the singular support is irreducible, really the Euler obstructions are no different from this intersection cohomology stuff. And this happens for the general matrices and for skew symmetric matrices. The singular supports are always irreducible, but for symmetric matrices, they can have two components. So somehow the symmetric case is a little more complicated because of that. Okay, so I guess I said we use this characters of simple modules. So let me just summarize the strategy for the calculation. So what we do is, well, we don't really do this now. We compute this matrix M of micro-local multiplicities. In fact, it's really not too hard to do based on the characters. Really just a simple observation plus the action of the Fourier transform on simple modules. So this, it's easy to see how the characters give you this matrix of micro-local multiplicities. And just what the conclusion is what I was saying earlier, that the singular supports are mostly irreducible when you look at general matrices or skew symmetric. So that means that the matrix M is a diagonal matrix. Maybe the entries are plus or minus 1. And then for symmetric is, well, sometimes is irreducible, or in the interesting cases, it has two components. When for some strat, I will have two components.
I do have a question.
Yes.
In the case that n is equal to m, what do you get? In the first, I mean, the characteristic cycle or singular support is going to be reducible as well?
Yes, yes, even for n equals n.
Okay.
So the point is that if you look, I mean, there's a theory that says that somehow this, well, so the cotangent to the rank I matrices, it's just pairs of rank I and co-rank I matrices whose product is zero based. So if you apply a Fourier transform, if you do a rotation, then you will get the cotangent of co-rank I matrices. And so now it's an easy calculation based on the character that if you look at the character of a simple module supported on I, and you do the Fourier transform just as a representation, then you get the character of a simple module supported on n minus I. And so somehow that leaves no room for other components in the characteristic cycle to appear. So, and it's regardless of whether n is n or.
Okay, thank you.
Oh. All right, so let's say these micro-local multiplicities are done, and then this is to be discussed how to compute the Euler characteristics. And then the final step is this one. Okay, so 2 is interesting, yeah. What is 2? So I'm saying I'm interested in computing these stock Euler characteristics. And there is a very familiar localization trick when you work with matrices that works for this calculation. And basically what it tells you is that up to a sign, this is the same as computing the Euler characteristic of the stock at the origin for a related variety of matrices. So this Vj minus I tilde is still a space of rank j minus I matrices, but of smaller size. Smaller size. And still rank with more j minus I. So basically, all you need to know is how to compute these stocks of intersection cohomology at the origin, and now there's a further argument when you have a C-star action on an affine space. You have this subvariety that's closed under the C-star action, and you want to compute the intersection cohomology stock at 0. That's the same as the global intersection cohomology. And I understand I've used this notation for the constructible function here. I don't mean the constructible function, I really mean the global intersection cohomology. The global intersection cohomology or the characters. And again, if you like the D module world, and this is the same as the global Theorem cohomology of the simple module associated to this subvariety J minus tilde inside a smaller matrix space, which we now call X tilde. So basically, X tilde is obtained from X, you drop I rows and I columns from your matrix. Okay, so really what our result is about is just about computing the RAM cohomology in this situation where you have a group acting with finitely many orbits. So let me just tell you the theorem that we used, and then there's some calculations afterwards, but maybe I will skip. So the theorem says, okay, so let's suppose G is connected. Inductive acting on X with finite many orbits. Then there's two statements. The second one is the interesting one. So the first one is just that for any equivariant polynomial D module, and you can compute the RAM cohomology. Of course, this by definition, this is the cohomology of the Theorem complex. So you look at n omega 1 tensor n omega small x tensor n. By definition, this is the ith cohomology of this complex. So again, x, the affine space. So this is a representation of G. And what we're saying is that, well, you can do this, but you can maybe first take G invariance. So just take the ith cohomology of this complex. So we call this the invariant of the Theorem complex. So this is not, this is just some general nonsense about the fact that you map to a point, computing the RAM homology is taking the push forward to a point, and then that maps is G equivariant, and so then it's clear that G is going to act trivially on the RAM cohomology. So basically, you can just first take invariance and then compute cohomology. Okay, but the more interesting case is that, so we know that whatever we're going to get at the end, the RAM homology groups are going to be finite dimensional vector spaces. But the more interesting case is, the more interesting fact here is that each of the terms in this invariant RAM complex are going to actually be finite dimensional vector space. So each term in this RAM complex is a finite dimensional vector space. So, of course, what's missing is a good tool of understanding I'm interested in the case when M is simple, understanding the structure of these modules as representations of G, and then once you have a good understanding of this, you can figure out exactly what these invariant terms are, and then you take an alternative sum, and there you go. You have this intersection, cohomology, whatever characteristics that you want. So let's just do an example to show you how things go. Again, I only know one example, I guess, quadratic cones. Let me try to do that. Okay, so to get the quadratic cone, I'll take my space to be symmetric 2 by 2 matrices. Of course, that's just a 3-dimensional vector space. This the coordinate functions on the matrix. And if you think about what the matrix stratification is, well, you have affine 3 space, this is your X, and then the rank at most matrices, rank at most 1 matrices means vanishing determinant, that's the 0 locus of a quadratic, that's this quadratic cone, and rank 0, that's the origin. So I guess this would be X0, X1, X2. So we kind of seen this example before. And so I need to pick a simple D module. So I'll pick I'll call it D1. This is the simple D module corresponding to the quadratic cone. So it's a simple supported and rank at most 1 symmetric matrices. And the calculation that I was talking about a few years earlier says, it tells you exactly how to decompose this. T1 has a direct sum of representations of GL2. Okay, so those representations are indexed by, the irreducible ones are indexed by two to a sequence of non-increasing. So lambda 1 is bigger than or equal to lambda 2. And to any such pair, you have an associated true functor that gives you a irreducible representation of GL2. And well, for reasons that will become obvious, I want to work with the duals. And so not all pairs show up, but it's just the ones where lambda 1 and lambda 2 are even, and lambda 1 is bigger than or equal to 2. So this is one sample calculation that tells you what the structure of D1 is as a GL2 module. Okay, so how about the modules of differentials? For this omega I, well, omega 0, just the generators maybe. Omega 0 corresponds to the trivial representation, that's generated by 1. Omega 1 corresponds to just C2. Oh, sorry, SIM2 of C2. So I guess I would write that as S comma 2, 0 of C2. Omega 2 corresponds to the second exterior power of S2, 0. And if you know just a little bit about Plato, you can see that this is S1 of C2. And then omega 3 is wedge 3 of S2. So one-dimensional, it's generated by one-dimensional representation, which is just S3. Okay, so we know what these guys look like. So then I want to compute the Theorem complex of D1 and take GL2 invariance. So what do? By the way, to be a GL2 invariant means you have to be a trivial representation. So the trivial representation corresponds to space 0, 0. So the invariant Theorem complex starts with a G invariance in D1. Well, there's certainly no 0, 0 right here because lambda 1 is at least 2, so 0, 0, not here. So that means that this guy is 0. What's the next one? Well, the next one is I have to do S20 tensor with with D1 and take invariance. So in general, because these sure functors determine irreducible representations of GL2, if you want to have G invariant inside such a tensor product, then it has to be that lambda and mu are equal. So then the G invariant space is one dimensional, just given by the unique isomorphism between S lambda and S mu, to scaling, and otherwise it's 0. So basically, if you're asking whether there is invariance in here, what you're doing is you're asking whether 2, 0 pairs among these pairs. And it does, because lambda 1 equals 2 is even in interface 2, and lambda 2 equals 0 satisfy this inequality. So this space is actually one dimensional. But if you do the calculation for the higher terms, well, then S31 is not going to appear in the decomposition of D1. So this guy is going to be 0. And likewise, S33 is not going to show. And so this term is also 0. And so actually the invariant around complex has only one non-trivial term. And then you compute the Euler characteristic. What you get is that chi 0, 1 is equal to 1. So again, let me emphasize this because I'm talking about rank at most 1 matrices, and I did a calculation of global Theorem cohomology, which corresponds to the stock at 0. Okay, and so you can imagine how this goes if you knew how the other simple modules decompose. So with some work, what we get is that this matrix chi is just 1, 1. So the previous page is the calculation of this number. And there's a few more to compute. So I told you that the matrix of micro-local multiplicities is easy to derive. I just want to emphasize this is not a diagonal matrix. The fact that you have 2 entries in this column is just a statement that if you look at the singular support of the IC sheaf of the quadric cone, or the characteristic cycle of the corresponding V module, it's going to have 2 components. That's the cotangent to V1 plus this cotangent for space of 0. Okay? And so then, with even more work, apply the local index formula, and then we're going to get the 1, 0, 1, 0, 1, 1, 0, 0. This was the first example that we looked at. Okay, so let me stop here.
Thanks. Does anyone have any questions for Claudiu?
Yeah, I have a question about the Kashivara index theorem. You have this form for intersection homology modules, but it works in general, right?
Yes, you could do any. Yes, I'm only computing it for the simples, but yes.
But in general, do you have this interpretation in terms of these matrices as well, or is more complicated?
So I mean, you can for any sheaf you can associate a singular support,
Mm-hmm.
and the local Euler characteristics. So I guess what I'm saying is I picked bases. So I picked, so for the perverse shifts, I just took the simple modules corresponding to that stratification. And then I get, inside the constructible functions, I just get just a free submodule generated by the indicator functors for the closure of the strata or this EUV, and then on the Lagrangian cycles, I just get this free submodule generated by cotangents to these, and all I did was to just write down the transfer matrices relative to these bases.
Okay.
So now, if you have a more general shape, you have to write it in terms of the symbols. Yes, I mean, this passes to the Grothendieck group, right? So it's enough to figure out how many IC sheaves show up and which multiplicities, and then you're going to be able to do this calculation.
Okay. But this is really difficult to find a composition series.
Yeah, okay, of course, that's a different question, yes.
Yeah. Okay.
So I guess that's an extra step to do. Yeah.
Okay, thanks.
I have a question.
Yes.
So the authors you cited, Gaffney, Grula, Ruas, they use Nash blowups to study Euler obstructions. So
yes.
The question is, these Nash blowups, are they hidden somewhere in your approach, in your work?
Certainly, we don't see them. So the point is that, there's all this work of people in the 80s that give this alternative D-module interpretation of this Euler obstruction. And so we just work directly from there.
Okay, I see.
So yes.
Okay, thank you.
So I mean, that the original definition of McPherson is using the Nash blow. And so well, that's a question whether you can just run all these arguments by starting with the original definition.
Okay.
So it's certainly not something we use. So.
Okay, thank you.
So I guess a question along similar lines, right? So here you have a favorite 2 out of 3 of these matrices, right?
In this case, yeah.
Yeah, I mean, are there situations where somebody might have a different, favorite 2 out of 3 to solve for the third?
So I think Bo and Fu, which I might have mentioned next time, their favorites were their favorites were this local Euler obstructions and the intersection cohomology stocks. So the point is that in the case of flag varieties, this intersection cohomology stocks come from cardinalistic polynomials, and then there's a theory for computing those. That's certainly a favorite matrix when you work with flag varieties, the chi. And then what Bo and Fu did was to compute this local Euler obstruction. And for instance, based on that, they figured out new examples of reducible characteristic cycles. So I mean, that's I think, as far as I understand, it's a serious open problem in geometric representation theory. I take a sugar stratification. I look at one of these ICs. How do you compute the intersection? The singular sport.
I see.
And whether it's irreducible or not. So then, people know how to construct examples of reducible ICs, but they don't have a good tool of understanding. So I guess if you're good with intersection theory, and Nash blowups, then you might figure out the Euler obstructions. And then the chi's are just coming from Kashivara's theories, and those are okay. And so you could, in principle, get a tool for figuring out these characteristics.
Okay,
But
great.
I'm not sure what direction is going.
Yeah, that's great. Yeah, thanks. But I had another question that maybe you were planning on saying something about next time, in which case just, say that. What do these Euler obstructions obstruct?
Well, I think, I guess I'm not the master. So I think there are obstructions to extending some vector fields, and then that has to do with the description of the Nash blow. And it's not a very algebraic obstruction, so then that makes me not the person to talk about. But it has to do with extending vector.
Okay, thanks.